Thanks, Corinna, and thank you, everyone. Hi, I'm Duane Costa. Let me take a moment to share my screen here. Can everyone see that? Okay. I'm a developer with the Environmental Data Initiative, and the topic of today's tutorial is using the Pasta Plus Search API. I'm just taking a moment here to find my next button. There we go. Okay. Last week, Mark Servilla gave a tutorial presentation that was a comprehensive introduction to RESTful web services, and he covered a broad range of Pasta Plus web services. Today, I will do almost the exact opposite by drilling down deep into a specific Pasta Plus web service method, the Pasta Plus Search API. Now, what are some of the possible motivations for learning and using the Pasta Plus Search API? First, we may want to build a custom search interface that offers some feature or behavior not found in the search interface offered by the centralized data portal. For example, we might want to build a query interface where the search results are always restricted to a particular geographic area, or perhaps a particular research project. Second, we could use the Search API to build a local data catalog. In this case, our program is not accepting query input from an end user, but we are constructing the query ourselves in our program and displaying a table of matching documents for our local site, including things like title, authors, keywords, and perhaps the abstract. We'll be delving deeper into this particular use of the Search API in an ESIP 2017 seminar 1 week from today, in which I'll be co-hosting with 3 other presenters. More on this later. Third, the Search API can be used for data mining, where EML metadata is the data to be mined, processed, or analyzed in some way. I've provided a few examples here, though I'm sure many other better examples could be easily imagined. The final motivation I would list is efficiency, in that using the Search API in your script or program or on the command line is often faster and more efficient than relying on the central data portal, where the results are displayed in HTML and paged 10 documents at a time. Throughout this presentation, I'll be referring frequently to a technology called Solr, which is the search platform that the Pasta Plus Search API is built on. Solr, in turn, is built on Apache Lucene search engine technology. Entire books, very thick books in fact, have been written about both Solr and Lucene. Suffice it to say that they are amazing technologies. I won't be able to cover them in great depth, but I think that by the end of this presentation, you'll have a good appreciation for what they can accomplish and how they're used by Pasta Plus. In this highly technical diagram that I've stolen from Mark's presentation last week, we see the high-level view of a client program sending a request to Pasta Plus via its REST API. Pasta Plus processes the request and sends a response back to the client. I include this here simply to point out that the Pasta Plus Search API is really just another web service provided by Pasta Plus, one of over 50 total, though I might argue somewhat special because of the richness of information it can return and at blazingly fast speeds. Looking at the web service topology in a bit more detail, we see that the centralized data portal, be it the EDI data portal or its sister web application, the LTER data portal, calls exactly the same Pasta Plus Search API that we'll be covering in this presentation. In other words, there's nothing inherently different or unique about the data portal search interface that can't be replicated in your own client program. In both cases, the client uses a web service URL that makes a request, interacting first with the gatekeeper component of Pasta Plus, which then interacts with the data package component, which in turn interacts with the Solr server. The search results are generated by Solr and sent back along the same route in reverse, arriving in the response body as XML. It's not all that important to understand the individual steps in this process, the main point being that whether it's one of the centralized data portals or your script or program or browser or curl command, they all interact with Pasta Plus using the same web service API. To understand the Pasta Plus Search API, I think it helps to break it down into 3 simple steps. First, we need to know what metadata fields are searchable in Pasta, because we can't begin to construct good queries unless we know the names of the things that are queryable. Second, we need to know how to compose a query and send it to Pasta Plus. And third, we need to know what we're getting back as search results from Pasta Plus and how to interpret it. With regard to indexing, it's important to point out that not all metadata fields documented in EML are indexed by Pasta Plus in Solr. For example, date-time attributes in EML are accompanied by format string elements to document the date-time format, year, month, day, hours, minutes, seconds, etc., of temporal data. The current thinking is that there are no viable use cases where an end user would want to search EML metadata based on the particular format of date-time attributes, such as YYYY-MM-DD. And so this field is not currently indexed in Solr. Let's start by looking at the queryable fields that Pasta Plus does store in Solr. These are the bits and chunks of metadata that Pasta Plus has extracted from the EML documents in its repository and indexed in Solr so that Solr can perform its searches based on the criteria we send to it and then return search results to us quickly and efficiently. The fields include a variety of different identifier values, such as the DOI, Digital Object Identifier, many string and text fields, as well as fields involving temporal and spatial criteria. I'll be demonstrating a number of examples to show how these fields come into play when composing our queries and in the XML search results that Pasta Plus sends back to us in its response. Next, let's look at how to compose queries. The formal documentation for the Search API looks simple enough. Using the HTTP GET method, retrieve the results from searching Pasta's EML data packages. But the richness of this web service is the portion that comes after the question mark, the query parameters. We will explore this further with several examples. In our first example, we compose a query using only 2 query parameters in our URL. The Q parameter says, here's the field and the text I want you to match. Keyword is the name of the indexed field that is being queried, and we want to match all documents that have the word disturbance as the value of at least 1 keyword. The second parameter, FL, specifies the field list we are asking Pasta Plus to return. In this case, we're saying that for each matching document, all we want to know is its ID value, such as EDI.1. This is pretty simple, right? Only 2 query parameters. Although unfortunately, I don't think you're able to copy this text off of my screen share window. If you could, then I would pause a few moments to allow you to copy and paste it into your browser's address box, because you would see the results return almost immediately. In this second example, we see a longer URL, this time with 8 separate query parameters separated by ampersands. The first thing to note is that this is a curl command that can be executed in a command shell such as bash on Linux or an MS-DOS command window on Microsoft Windows. We're asking curl to run the get HTTP action, and we pass in the URL. The entire URL in this case has to be surrounded by double quotes to prevent the command shell from interpreting the ampersands within the URL as special characters to the shell. And this is true on both Linux and Windows. The first query parameter is quite long. Q equals %22 air plus temperature %22 plus and plus title : Arctic. Let's unpack this. We want to match the search phrase air temperature as a single search phrase, which is why we put quotes around it, not as 2 separate words. If it's found anywhere in the document, not in any specific field. And we also want to match Arctic, but it must be found specifically in the title field. Note the URL encoded characters around air temperature, as well as the plus sign between the 2 words. %22 is the URL encoding for double quotes, which was necessary here because we already have a pair of literal double quotes surrounding the URL. Next, the plus sign is used within URLs to represent a space character, or you might also see %20, which represents the same thing. The second parameter, FQ, stands for filtered query. It's just like a Q parameter, except that it does not count towards the relevance score. So it's a way to filter, including or excluding documents from the search results based on query criteria without having those criteria factor into the relevance scoring. In this case, note the negative sign in front of scope. This means exclude all matches that have the scope value of ecotrends, which is something you might want to do if you didn't want your search results to include any of the 15,403 documents from the Ecotrends project. If, on the other hand, you wanted to include only Ecotrends documents in your search results, you would remove the negative sign. FQ is also very useful when filtering based on spatial or temporal criteria, and we'll see some examples of that later. The third query parameter, FL, is asking for Solr to return a field list that includes the package ID, title, and score fields. Note that the score field is not metadata that we've indexed in Solr, but it's the relevance score, a floating point value that Solr/Lucene has dynamically calculated for each document based on how strong a match the document was to our search criteria. The higher the score, the stronger the match. With this in mind, the next query parameter asks that search results be sorted by score in descending order. And this makes sense in most search interfaces where you'd of course want to display the most relevant matches ahead of less relevant matches. In the case of ties, we have a secondary sort based on package IDs in ascending order. Next is a cryptic-looking query parameter, deftype equals edismax, and I'll explain that on the next slide. The final two, start equals 0 and rows equals 10, asks for Solr to return the first 10 rows, which starts at index 0. If we were implementing a web application that pages through its search results 10 documents at a time, we would first display these first 10 documents to the user, and if the user were to then select the next button, we would rerun this query, but this time specifying start equals 10 and rows equals 10. This, in fact, is exactly how the centralized data portal behaves. Now, if you were to omit the start and rows parameters, start equals 0 and rows equals 10 are the default values, so that this is what you'll get every time. This is what you'll get back every time you rerun the query. Although this is a much longer example, you could, if you're ambitious at typing, type all of the URL text, excluding the outer pair of double quotes, into your browser's address bar and watch it execute. The deftype, which stands for default type parameter, instructs Solr on which of 3 possible query parsers to use in processing the query. My admittedly limited understanding of this is that we have 3 choices. Leave out the deftype parameter and Solr will use what's called the standard Lucene query parser by default. Or use a variation of that parser called the disjunction maximum or dismax parser, which has, however, since been deprecated by a newer version called the extended disjunction maximum or edismax parser. So in practice, we're really choosing between the standard parser and the edismax parser. The data portal always specifies deftype equals edismax when processing user queries because the edismax parser is reputed as being better at processing user input in that it's more fault tolerant than the standard parser. That's about the full extent of my knowledge on query parser types, so I'll move on. The third key to understanding the Pasta Plus Search API is to understand how the search results are structured. Pasta Plus returns the results as XML. In this example, we've run a query that effectively says, give me all the fields you've got stored for the matching documents, which in this case is guaranteed to be a single document, the document with package ID of knb-lter-nin.1.1. The top level result set element shows that one document was matched as we expected. Within the result set element, there is a single document element, and within that document element are all of the individual fields that PASTA has indexed in Solr for this document. I think most of them are self-explanatory, DOI, abstract, for example, but note that we have some temporal coverage fields, begin date, end date, and also the publication date as pub date. Continuing on, we also see spatial coverage containing one or more bounding box coordinates. We see individual keyword elements wrapped by an outer keywords element. There are also empty fields visible in these results, for example, taxonomic, single dates, and timescales. These are cases where these metadata fields were not provided in the original EML metadata, so there was nothing to index. Working with these search results is a matter of parsing out the fields that you're interested in from the XML. For example, when displaying search results for an end user, you might want to include the title, abstract, authors, and keywords, and perhaps the DOI or the package ID. So those are the fields your script or program would need to parse from this XML. In the last two lines of the XML, we see the closing tags for the single document that was matched, and then for the entire result set element. Now that we have a pretty solid understanding of the PASTA Search API in all three of its aspects, which fields are indexed, how we compose queries, and what XML results are returned to us in the response, I'd like to take a moment to describe an alternative method for searching and retrieving PASTA metadata, what I'll refer to as the list and read APIs of PASTA Plus. Last week, Mark presented a number of PASTA Plus web service examples that involved listing scopes, identifiers, and revisions, and then another web service method to read the XML metadata for an individual data package based on its scope, identifier, and revision values. So it is entirely possible to write a script or program that, through a series of PASTA Plus web service calls, finds the set of data package identifiers you're interested in, perhaps all the data package identifiers within a specific scope, including older revisions of those data packages, and then reads each of those data packages one at a time, parsing and extracting whatever metadata from them that you're interested in searching on or doing additional processing on. Although this sounds like more work than using the PASTA Plus Search API, and in fact it generally is, there are some use cases where this might be the preferred approach. So let me compare and contrast these two approaches. First, with the Search API approach on the left, it's generally one and done. One call, one web service call to the Search API returns everything you need in one shot. It's fast, where even complex queries execute in a flash. You can query on spatial and temporal criteria. It takes advantage of all that sophisticated Solr and Lucene query logic. However, there are a couple of disadvantages. We're limited to the newest revision of any data package only. We do not consider older revisions searchable, and so they are not indexed in Solr. When a new revision comes in, it replaces in Solr the previous revision. Also, we are limited to the queryable subset of EML content, things I've already mentioned, title, keywords, abstract, etc. Not all of the fields. Contrasting that with the alternative list and read approach, that could require hundreds or even thousands of calls to PASTA web services to list all of the package identifiers and then read the individual metadata documents you want to process. This could take several minutes to execute. There is no built-in capability to query on spatial or temporal criteria. You would need to program that yourself. If you need any kind of query criteria, you would provide the logic by programming it yourself. However, you could access all revisions, not just the newest, and you could access all parts of the EML content, including that format string example I gave earlier that is not indexed in Solr. Could also envision using a combination of the search API approach and the list and read approach for certain use cases. The Pasta Plus search API is not necessarily set in stone, and we are always open to considering enhancements to it. One obvious enhancement would be to add to the set of fields that are currently being indexed. Perhaps there are some fields we've overlooked that really should be indexed so that they can be made searchable. Doing this is not too difficult for the Pasta Plus developers. It requires some relatively minor code changes, some testing, and then a complete re-indexing of the entire repository of EML metadata documents in the Pasta Plus, in the EDI repository, which is an operation that requires about 10 to 12 hours, so we run it overnight. Second, we haven't talked about the XML that the Solr server itself returns, which is structured quite differently from the XML returned by Pasta Plus. To my eyes, anyway, we've structured it in a much simpler, more intuitive way. However, there might be cases where some clients of the Pasta Plus search API are more comfortable parsing search results returned in the native Solr XML format. If there is a demand for this, we could potentially provide that as an alternative to the Pasta Plus XML format, probably by offering a separate web service API just for that purpose. And finally, if you think of other helpful enhancements or come across any bugs that need fixing, please feel free to let us know. Contact information will be provided in a resources slide at the end of this presentation. I'd like to sneak in a plug for an upcoming seminar at ESIP 2017, 1 week from today, titled Using Application Programming Interfaces of Data Repositories to Create Local Data Catalogs. Although there will be some overlap in that seminar with what was presented in today's tutorial, it will focus more specifically on the purpose of creating local data catalogs. My co-presenters, Stephen Earle, Gastel Buell, and John Porter, will delve deeper into this use of the search API, providing actual use cases and examples of how search results that are returned by the Pasta Plus search API can be processed and rendered as HTML that can form the basis of an attractive local data catalog for your site's end users. If you're able to attend, then I hope to see you there. Here are a number of resources with links included. The Granger and Potter book listed at the bottom, Solr in Action, is one that I have found particularly helpful, and I highly recommend it to those who are interested in learning more about Solr and Lucene, because it goes into much greater depth than I've had time to cover today. Before I end my slide presentation and transition to my Jupyter Notebook demo, I'd like to say thank you and happy searching. And now I'd like to demo a wide assortment of Pasta Search API queries using Python and Jupyter Notebook. Oops, I have to get out of my full screen mode here and switch here and back to full screen mode. Here we go. Can you see that okay? All right. So at the very top here, I want to emphasize that the point here is not to instruct in using Python, but to use just enough Python to get across how one approach to using the Pasta Search API programmatically. So at the very top, we're going to tell Python to import the third-party libraries we need to make this happen, and there's really only one. It's called the requests library. So I'm going to run this and import requests. Next, we're going to define our base URL, and this is everything that comes before the question mark in our search API, and it never changes, so it will always be this value. So I'll run that cell and make that happen. Now we're going to get into our actual examples. In our first example, I had this up on a slide as our first example as well. Match all the documents with keyword disturbance and display their IDs. Let's see what happens here. So we found 12,003 matches, but because by default start is 0 and rows is 10, we're only displaying the first 10, one from Lucia and all the rest from Servietta. So there we have our list of documents, And within each document, we've only asked it to display the ID field. Next, let's run a query where we're going to match anything in Pasta Plus, in the EDI repository, I should say. Q equals star. Star is a wildcard character, so it says match anything. However, give me all fields as well. FL equals star. Here's another use of the wildcard. However, only give me one row. So we're going to match everything in the repository, but we're only going to display the first result. So let's run this and see what we get. And we, in fact, did match 42,381 documents, but we're only displaying one of them, thank goodness. And it happens to be from Kellogg Biological Station, KBS. Okay, here's a use case that actually came up recently. Find all Florida Coastal Everglades data packages displaying the package ID, the title, and the DOI. So let's run this one. And we've matched, oh, this time we asked for the first 1,000 rows, so we should get a bigger result set. In fact, we did. We found 159 matching documents, and we've got all of them here, but for each one, we're displaying the package ID, its title, and its DOI. Here's an alternative query that does the same thing, but this time I'm using the filter query because this is a case where it's not really important that the scope value of KNB-LTR-FCE be counted toward relevance scoring. So I'm going to say Q equals star, match everything, but filter, give me only documents where the scope of KNB-LTR-FCE. So this is really the same query. We should get the same result. But this time we've moved the real queryable thing into the filter query instead of the queue. And in fact, we have those same 159 documents in our result. Here's a very long example. Match, I believe this is pretty much identical to what I had on our slides. Match the phrase air temperature anywhere in the document and Arctic, specifically in the title field. Exclude Ecotrends documents. Sort on score descending and secondarily sort on package ID ascending. Use the EDIS Max query parser and display the first 20 rows. So I have to scroll over so you can see that whole query, but I think I've already explained all of this in the presentation, so I'll just go ahead and run it and see what we get. So all of these documents should have Arctic in their title because we specifically asked for that. Somewhere within the document, we're pretty confident is the phrase air temperature, but we've only asked to display the package ID, the title, and the score. And so we've sorted the score in descending order. We can see that the high score here is 1.76, so forth. And from that point, they get lower, they're descending. In the case of ties, they should be sorted by package ID. And here's a tie. In fact, several of them have the same score, and we should see that these are in fact sorted by package ID. It looks like they are. Okay, this time let's find disturbance anywhere in the document, but filter on the EDI scope. The Q parameter counts towards relevant scoring, but remember the FQ parameter does not, otherwise they're pretty much the same. So we're looking for EDI scoped documents that have disturbance mentioned somewhere in the document. And we came up with one match, EDI.15. This time we're going to query on author, and we're going to ask whether Duane Costa has authored any EML documents. We're trying to match Duane and Costa, but not as a single phrase, but we're specifically saying you have to filter only on author Costa. The last name Costa has to be somewhere inside author, and we're going to ask for ID, title, author, and score. So let's run this one. And lo and behold, I have been credited with authoring a few of these EML documents, thanks to the generosity of my co-authors. So you see that I am listed here as an author for the first three. However, for this fourth one, I'm sure that Scott Costa is a much better author than I am, but in this particular query, he came up with the lowest score because it was not as close a match. What do we have? 4 more to go here. How are we doing on time? 11, not too bad. Okay, here's a long one. Query on subject, primary production, or subject plant. Now, note that subject is not in EML. It's an aggregation of several other fields that contain searchable text. So we take author, organization, title, keyword, and abstract, and roll that all together into something, a single searchable field called subject. So I'm asking for the subject can be primary production, in which I've enclosed in quotes, or it can just be the word plant. And let's see what we come up with. Oh, I have to click on that cell and then click this, and there we go. We came up with 1,810 matches, but we're only displaying the first 10 here. For a field list, I asked for ID, package ID, title, author, organization, pub date, and coordinates. I also said debug equals false. I don't think it's really necessary to include that. I asked for 10 rows, and I asked for sorting by score descending, and I did use the default type parser of edismax. Okay, three more to plow through here. First, temporal criteria. I've composed a query that says, find everything with temporal criteria between the 2-year period of January 1st, 1995 through January 31st, 1996, where the begin and end dates must fall within that 2-year period. Okay, I think this query is a little complex. I'm not sure there's time to go into it in detail or whether you'd want to hear me go into it in detail, but there are ways to construct these temporal queries. Perhaps you could contact me out of band if you need to do this at some point. The way I've constructed this particular query is to ensure that the temporal criteria always fall within that 2-year period, nowhere outside of the 2-year period. So let's run this and see if it works. And if we look at either the single dates that are returned or the begin dates and end dates, they should all occur within that 2-year period. And I think I'm seeing pretty good results here, at least in the first 10 that are displayed. Here's a similar query, but this time I've restructured my temporal criteria. Once again, very complex, probably not worth going into here. But this time I'm saying that it can match, it has to include or overlap that 2-year period, but it can also be somewhere outside of that 2-year period. And I'm using qualifiers that Solr accepts, such as the now qualifier to implement the current date and time right now. And also an asterisk as a wildcard to represent any date and time or the beginning of time. So it's asterisk to 1996 and so forth. Pretty complex. I just wanted to include it here so you can see that it can be done. And in fact, the data portal does use this in its own temporal search. And now we're seeing dates that overlap that 2-year time period, but do include it. Oh, we've got one from 1891 to 2006. That's very long term. Okay, and finally, some spatial criteria. I'm asking for everything that matches within a given bounding box coordinates. And here are the coordinates. And I'm using a keyword that says is within. Just a side note here, this was the keyword that's used in Solr 4.10.2. I think I saw some documentation that more current versions of Solr, it's up to Solr 6. Something at this point, might now be using within instead of is within. But regardless, what this is requiring is that the spatial coordinates fall within these 4 coordinate values. And I'm asking for the three rows to be returned. And here we go with our last example. And we can see that it did in fact match 345 documents, but the first 3 displayed here are from Virginia Coast Reserve. Excuse me. All right, that concludes the demonstration part of my presentation. And at this point, I'll turn it back over to our moderator, Corinna, for questions and answers.
Thank you, Duane. So I'll open the floor for questions, and I see Stace has one. Go ahead.
Hi, Stace.
That was so awesome. So it's really great. I'm sure our new site is going to be testing this for you later this year. But I have two questions. So the first one is, I'm wondering why do you have to specify subject? Because you use subject primary production, but earlier you just used look for the word air temperature. So what happens when you just look for a free text? Does it search all fields or just like title? What is it searching?
Yes, free text would be all text and string fields that are indexed, whereas subject would be, you might get a more relevant result by searching on subject because it is a conglomeration of some of what we might consider the more important searchable fields like title and abstract and keywords.
Okay.
And so you could search on subject if you thought that it was more important for your matches to be contained in those fields as opposed to, say, in something like methods, which is not included in subject.
Oh.
Or if you were documenting the project, which is not specific to this document, the project may contain some terms that you want to avoid matching, or you want to avoid them being calculated high in the relevance scoring. So you could avoid that, that lesser important field by using subject as a searchable field.
Okay, one more quick thing, because that totally makes sense. So in the very last example you gave with the is within,
Yes.
just because I work with geospatial so much, like I always recommend choosing an example with a longitude that's greater than 90, because when you do see that, you don't know which is the lat long order. Do you know what I mean?
Oh, okay, yeah, I know this can be tricky. You mean in terms of avoid negative values? Is that what you're saying?
No, it's just that like when I'm like an outside user, I've never used this API yet, but it's not indicating to me the order in which to put the lat or the lon, and if you just use a number greater than or less than -90, then I know it's longitude.
Oh, I see. Okay, good advice.
I've come across that so many times.
I obviously don't work with this nearly as often as you do. I wonder if we should check how the data portal has been programmed to use this. But I think the data portal results have been accurate based on my testing. But I'll probably revise this example based on your advice. So to be clear, you're saying it's the longitude greater than 90, not to worry about the latitude, right? That can't be greater than 90. Right, okay.
Thanks so much.
All right, thanks.
So I can't see everybody. If you just want to speak up, please go ahead.
I hope I didn't overwhelm everyone with too many examples. If you made it through, congratulations.
Well, if there are no other questions, going one, going two, going three, then thank you very much. And especially thank you to Duane for a very nice presentation. That was awesome and really clear, and I'm really looking forward to looking at that Jupyter notebook.
I'm very new to it, but I found it easy to pick up.
Yeah, it looks really cool. All right, so I'll stop recording here, and then I'll turn